Hi there, we'll be explaining our project today, which is on game sales and ratings. Here's the table of contents. So, why did we pick this topic? Game developers today develop large-scale games with immense budget. I'm sure all of you have heard or played GTA 5 before. But did you know they had $265 million of budget to produce a game? How do they know if they're going to make money on their game? Or will they make a loss? This is where we come in by taking the critic scores of the games to predict the global sales of the game. Now we'll be going through how we collected the data and prepared the data for machine learning. In order to gather enough data for a project, we had to write scrape data from VG charts and another publicly available Metacritic dataset. VG charts is well known to collect reliable game sales data, but Metacritic is a world-renowned game critic site. As mentioned before, we had to learn how to scrape data from the web. We used Beautiful Soup and the respective websites API to obtain the data that we required. However, because this dataset only has 2 scores, it is insufficient for us. That is why we obtained the Metacritic dataset to supplement it. We then used a publicly available dataset from Metacritic that was available on Kaggle to gather more information about critic and users' reviews. We did not scrape Metacritic's website, and the dataset had data for games from 1995 to 2021. We responded with the data we scraped from VG charts. To prepare the data for merging, we renamed the columns so that they'll be easier to identify. We also removed the rank column as it was not useful to us. We also renamed some columns in the Metacritic dataset so that it is more identifiable and it will merge seamlessly with our other dataset. In order for the merge function to work effectively, the platform column needed to have the same unique values. So we changed the values of the Metacritic dataset to match those in the VG charts dataset. We merged the datasets using the .merge function to obtain the final dataset that we will be working with. The example of the final dataset is shown. After merging the datasets, we now process and clean the data. We assume the null values in sales regions means there was no sales, so we replace them with zeros. Moreover, we dropped the rows with null year to help with plotting graphs later. We also converted a type of meta user review to float instead of object. Now that we have our data, let me pass the time to Kamin, who will go on with the exploratory data analysis.
Thank you, Vignesh, for that introduction. Now, we will move on to exploratory data analysis. To learn more about the data, we first described it as a whole. We then continued to plot a bar plot, histogram plot, and violin plot of the columns to see the distribution of the data. The graphs are shown here. We realized that the skew of the sales was very bad due to many large outliers. So we removed them and took another look, achieving much better results. We then plotted a heat map and a pair plot to try to visualize the correlations. However, we realized that most of the numerical data only very weakly correlates with global sales, and we will not be using regional sales as indicators because they simply sum up to give us global sales. After the numerical data, we move on to look at the categorical data. We first looked at the counts of each genre and did a cat plot of genres against regional and global sales to see if there is any regional or global preference for genres. The graphs for global sales are shown here. After looking at the genres, we looked at the counts of each platform. We then did a cat plot of platforms against regional and global sales to see if there is any regional or global preference for platforms. The graphs for global sales are shown here. We realized that there is no obvious regional or global preference for platform or genre, and that the data is generally weakly correlated due to the overlaps shown in the cat plots. Lastly, we tried to find the games with the highest sales each year to see if we were able to learn anything more. However, unfortunately, we were unable to glean any more insight from them. Now, I'll pass the time to Adrian, who will go through our machine learning section.
Thanks, Kamin. Now, we'll talk about the models that we've created using machine learning to predict global sales. For this project, we've created 2 models using 2 different libraries. One using CatBoost and the other using TensorFlow. So why use CatBoost? One of CatBoost's core edges is its ability to handle categorical data, opposed to the majority of other machine learning algorithms that cannot handle non-numeric values. From a feature engineering perspective, the transformation from a non-numeric state to numeric values can be a very non-trivial and tedious task, and CatBoost makes this step obsolete. CatBoost builds upon the theory of decision trees and gradient boosting. The main idea of boosting is to sequentially combine many weak models and thus through greedy search create a strong predictive model. For our second model, we'll be using TensorFlow to create a deep neural network model. So, why use TensorFlow? TensorFlow gives us more flexibility on how our hidden layers are built. It provides many customizations and allows the user to choose, for example, the number of nodes in each hidden layer, the activation function, the loss function, and the optimizer that we want to use for our model. In addition, Keras, which is a high-level neural network library that runs on top of TensorFlow, makes it easier to do so. Now, looking at our CatBoost model, using variables such as name, platform, year, genre, publisher, and metascore to make our predictions. After many combinations of different learning rates, iterations, and loss function, we found that with a learning rate of 0.001, with RMSE as our loss function, and running at 10,000 iterations provided us the best results with a RMSE of 214,000. Even though that might seem like a very high number, the data collected from global sales ranges from 10,000 to 1,120,000. Therefore, a RMSE of 214,000 would still be within a reasonable range. Before we review our TensorFlow model, we need to learn to understand learning curves to review the performance of our model. And the most common way is to observe the training loss plus validation loss over time. The training loss indicates how well the model is fitting the training data, while the validation loss indicates how well the model fits into new data. On the left shows a model that is underfitting. When that happens, it usually means that the model is unable to capture the relationship between the input and output variables accurately. Or we simply do not have enough data. Another possible reason could be because the number of nodes and layers is too low, or the learning rate is too low. On the right shows a model that is overfitting. When the validation curve starts to go in the opposite direction away from the training loss, we can tell that the model is learning unnecessary data, which is affecting the model's predictions, thus overfitting. We can combat this by decreasing the number of nodes or layers, adding dropout layers, or decreasing the learning rate. In the middle shows a model with good fit. The idea is to get the training and validation loss as low as possible while getting the validation loss to be as close to the training loss as much as possible. When the curve starts to stagnate, we can tell that the model is no longer learning from the data, and that's where we can stop the training process. Now, unlike CatBoost, TensorFlow does not allow us to simply use categorical variables as input. To fix this, we need to one-hot encode certain variables before training. Because of this, we decided to drop names, as names are all different and they would each create their own category, which could increase the difficulty of the problem. Therefore, for our second model, we will only be using platform, metascore, year, genre, and publisher to make our predictions. With the parameters of our model stated on the left, we managed to get the best learning curve of our model, which is shown on the right. With an RMSE of 224,000, both the CatBoost model and the TensorFlow model achieved very similar results, with CatBoost model outperforming the TensorFlow model ever so slightly. With this, I'll be passing on to Vignesh, who will talk about our conclusion for this project.
To conclude, contrary to popular belief, game ratings do not determine game sales. There is a big correlation between ratings, platform, and genre when compared with global sales. The root mean square value is slightly high when compared with the range of our test data. There are also other factors in play that affect sales, such as marketing strategies. Hence, these categories should not be the primary indicators for predicting global sales.
We've now come to the end of our presentation. We hope you've enjoyed it and learned something from it. Thank you.